Hello and welcome to our presentation on Eco-Design Engineer for Solid. This is part one, and in part one, we will provide an introduction to the concept of lifecycle assessment. Eco-Design Engineer is a 3DEXPERIENCE platform role that contains applications that allow users to perform lifecycle assessment on their products. If you are familiar with lifecycle assessment, then feel free to skip to part two or part three of this series. So just a brief overview of Eco-Design Engineer. Eco-Design Engineer is a 3DEXPERIENCE platform role for lifecycle assessment. And the type of lifecycle assessment performed in Eco-Design Engineer is called process-based lifecycle assessment. Eco-Design Engineer is a role in the greater sustainability innovation intelligence offerings available to 3DEXPERIENCE platform users. So what is LCA? LCA, again, stands for Lifecycle Assessment. LCA is a technique to assess the environmental aspects and potential impacts associated with the product, process, or service. You perform an LCA by first developing an inventory of the inputs, and these inputs can be energy and or material, and then you develop an inventory of the releases or outputs from a particular product, process, or service. This inventory is referred to as the lifecycle inventory. Then you calculate the environmental impacts of each of these inputs and releases. And finally, you would interpret the results. And this is the definition for lifecycle assessment as provided by the US EPA. One thing to note is that lifecycle assessment encompasses the entire product lifecycle or the entire lifecycle for a process or service. It can include raw material extraction, manufacturing, any packaging and transportation for your product or service. It includes the use phase emissions, what we're calling product as a service, and of course any environmental impacts associated with end-of-life treatment, particularly for a product. So let's say you're disposing of the product, sending it to landfill or having it be recycled. For an example of a life cycle assessment, let's consider that we would like to perform a life cycle assessment on a paper cup. This is a simplified representation of the life cycle inventory. In the middle, we have the paper cup itself. On the left side, we have all the inputs that went into creating the paper cup and delivering the paper cup, let's say, to a store where it was purchased. On the right side, we have the waste associated with disposing of paper cups. So clearly, we can refine this life cycle inventory by adding more inputs. And so we'll say that we're going to add one paper cup's worth of 12 weeks of storage. So let's say the paper cup is stored in an air-conditioned room at a store where you purchase it, and one paper cup's worth of 1,200 miles of transportation by truck. So you can imagine a large truck carrying perhaps 1 million paper cups, and so we're going to account for one paper cup's worth of that 1,200 miles of transportation from the factory where the paper cup is made to, let's say, the store where it is purchased. And then on the right-hand side, when we throw away the paper cup, that's 5.7 grams of paper being sent to a landfill. We'll consider these to be the level 1 inputs in our life cycle inventory. And of course, we can think of refining our life cycle inventory even further. You can imagine there being one paper cup's worth of equipment depreciation, and this is equipment used to manufacture the paper cup. There's one paper cup's worth of paper pulp, bleach, and of course the energy required to produce one paper cup at the factory that produces paper cups. And so these would be the level 2 inputs. One rule of thumb in life cycle assessment is that generally, if you go beyond 6 levels from the product itself, either in inputs or releases, if you go greater than 6 levels, then the individual contributions of the items in the lifecycle inventory tend to have very little impact. That you're really going into minutia when you go more than 6 levels away from the product. And so most lifecycle inventories include no more than 6 levels, and many include perhaps fewer than 6 levels. And each of these individual items in the lifecycle inventory has an associated environmental impact. There's environmental impact associated with equipment depreciation, environmental impact associated with getting the paper pulp, the 12 weeks of storage, and of course, environmental impacts associated with disposing of the paper cup and sending 5.7 grams of paper to landfill. To review, the life cycle assessment process involves first defining the inputs and outputs to your product, process, or service. And this definition of the inputs and outputs constitutes the lifecycle inventory. And then for each item within the lifecycle inventory, you would calculate the environmental impact in order to develop a lifecycle assessment. And this represents process-based lifecycle assessment And one note is that these life cycle inventories can include a large number of inputs and outputs. Looking here, this is a simplified representation of the life cycle inventory for a cell phone. And so going left to right, the bluish squares, that's extraction of raw materials. For example, on top, it's extraction of iron ore. The next level, these greenish squares, that's the production of the material itself. So from iron ore to iron. The next level, those bluish gray squares, those are the production of the individual components of a cell phone. So the microphone, the speaker, the antenna, things like that. Then those yellow squares are the life cycle inventory items for the assembly of these components to ultimately produce the cell phone. And then if we move to the right one more time, those bright green squares are the use phase of the cell phone, right? So it's recharging the battery, it's the use of the cell phone, repair of parts. Of course, this should also include use phase impacts when you access information through your cell phone on the internet. Finally, the last set of squares all the way on the right are the end of life treatments for the cell phone. So cell phones can be recycled, they can be reused as part of a take-back program. Sometimes they get incinerated, sometimes sent to a landfill. So that's the end of life treatment for the a cell phone. And so again, this is all the inputs and outputs. And for each one of these squares, there is an environmental impact, and the aggregation of these environmental impacts constitutes the life cycle assessment. Next, let's discuss the environmental impacts that are calculated in life cycle assessment. The first environmental impact, and you may also hear me refer to these as environmental damage categories or impact categories. The first environmental impact is greenhouse gas emissions. So, of course, we all understand that an increase in greenhouse gases in the atmosphere increases radiative forcing, which traps heat in the atmosphere. The unit for greenhouse gas emissions when it comes to life cycle assessment is often kilograms of carbon dioxide equivalent. This notion of equivalence refers to the fact that the 7 greenhouse gases each have a different global warming potential. That is, they each cause a different level of radiative forcing per unit mass in the atmosphere. And we use this idea of equivalence so that we can report emissions of the 7 greenhouse gases as CO2 emissions. And that simplifies the reporting of greenhouse gas emissions. Note that you often see for greenhouse gas inventories, that is the carbon footprint of a larger organization, you often see the unit as metric tons of CO2 equivalent. But for life cycle assessment, it's kilograms of CO2 equivalent. The next environmental impact is non-renewable energy consumption. As a non-renewable resource, there is concern of over-exploiting this resource and not having fossil fuels available in the future. And the common unit for this environmental impact is megajoules. Another environmental damage category is water eutrophication. An overabundance of nutrients deposited in waterways and streams and lakes through, industrial processes results in excessive biological production that basically consumes the oxygen in the waterway and chokes the water and makes it uninhabitable for fish. Water eutrophication is measured in phosphate equivalent or in kilograms of nitrogen equivalent. Again, this notion of equivalency. And whether you're using phosphate equivalent or nitrogen equivalent depends on your LCA calculation methodology. And we'll go into that a bit later on in this presentation. Next is air acidification, so the release of sulfur dioxide and oxides of nitrogen into the atmosphere from industrial processes, goes up into the atmosphere and then falls back down as rain with a lower pH than would normally happen. So it's acid rain. It can cause damage to plant life and man-made stone structures, but really the biggest concern with air acidification is the release of poisonous minerals that are commonly embedded in soil. And so as the acid rain falls, it tends to release those embedded minerals, things like aluminum and mercury and things like that. The unit for air acidification is kilograms of sulfur dioxide equivalent or moles of the positive hydrogen ion equivalent, again, based on your calculation methodology. And we're also, again, seeing this notion of equivalence. And there's many other environmental impacts. There's disability-adjusted life years, which is a measure of impact on human health, ecosystem quality, which considers extinction rates caused by human activity, potable water consumption, and many others. And again, the calculated environmental damage categories depends on your environmental method. And there are many environmental methods. These are the environmental methods used in Eco-Design Engineer. It includes the IPCC, or the Intergovernmental Panel on Climate Change method, that focuses on carbon dioxide emissions. There is EF 3.0, which is the European Commission Environmental Footprint Calculation Methodology. There's another called Recipe, EPS, or the Environmental Priority Strategies. And even the US EPA has the Tracy environmental method, which stands for the Tool for Reduction and Assessment of Chemical and Other Environmental Impacts. Now that we understand the environmental impact categories, we should answer the question how you use a life cycle assessment. There's two common uses. First is to find hotspots within your product, process, or service. You use the LCA to identify the largest sources of environmental impacts, which should guide your decision-making in determining where to make improvements to your product, process, or service. One of the most popular uses for LCA is comparative LCA, where you take two alternatives and determine which is greener. So it could be your older product compared to your newer product, your product compared to a competitor's product. It is very common to use comparative LCA in marketing and to differentiate one product from another. First, let's talk about using LCA for hotspots, and we'll look at two examples. The first is the example of a US company that worked with a tanning facility in Spain to process US cow hides to produce Spanish leather. This organization would acquire US cow hides in the United States, ship them overseas to Spain, and those cow hides would be processed into Spanish leather or finished leather goods and sent back to the United States. And this resulted in a considerable lead time. And so this company wondered whether or not it would make sense to open a tanning facility within the United States. Financially, there wasn't a significant savings in doing this, but the company asked whether or not it was more sustainable. So they performed a life cycle assessment for their Spanish leather. And what they found is that the environmental impacts associated with shipping the leather to and from Spain and having it processed in Spain were trivial compared to the environmental impacts associated with farming and raising the cattle used to produce the cowhide. In the next example, we can look at the typical American diet. So this is from the National Health and Nutrition Examination Survey that was run in the years 1999 to 2000. And in this survey, they asked adults what foods comprised their diet. And so we're looking at the top 10 foods that comprise the typical American diet based on a percentage of total calories, right? So sweets and desserts make up the highest percentage of calories in the American diet, then beef and pork, then bread rolls and crackers, mixed dishes, and so forth. And so you can imagine performing a life cycle assessment on a basket of foods that represents the typical American diet as we see here. These were the foods that were entered into an LCA to understand the total life cycle impact of these foods. These are the results from that food LCA, and we can see a hotspot in resource consumption related to cooking the food, so consuming natural gas. But really the biggest hotspot is associated with beef consumed in the typical American diet. For comparative life cycle assessment, where you're comparing one product versus another, one service compared to another service, an important concept is the concept of a functional unit. The functional unit is the unit that allows for different products or services to be equivalent. In this example, we're looking at a paper cup versus a styrofoam cup versus a plastic tumbler and a ceramic mug. For these products to be equivalent, we define the functional unit as the ability to carry 12 ounces of hot fluid for 3 hours, 500 times a year. And so you would need 500 paper cups, 500 styrofoam cups, but you would really only need one plastic tumbler and one ceramic mug, but you would have to consume resources in order to clean the plastic tumbler and the ceramic mug on a regular basis. So these are the results of a life cycle assessment comparing paper cups to styrofoam cups to ceramic mugs using that functional unit. On the left-hand side, we see the greenhouse gas emissions associated with consuming 500 paper cups or 500 styrofoam cups, or using one ceramic mug and washing it frequently. And we see that the ceramic mug still comes out way ahead, even considering environmental impacts associated with washing the ceramic mug. On the right-hand side, we see the non-renewable energy consumption associated with producing 500 paper cups or 500 styrofoam cups or one ceramic mug. which also includes energy consumption used to wash the ceramic mug. And we still see that the ceramic mug comes way ahead with regards to non-renewable energy consumption. There are other applications for life cycle assessments. One is the development of environmental product declarations. Many of you may be required to produce EPDs for your products. And life cycle assessment is the calculation tool used to understand the environmental impacts of your product. Another example is product carbon footprint. And again, life cycle assessment is the calculation tool to define a product carbon footprint. Let's look at some examples of environmental product declarations and product carbon footprints. So here we're on the International EPD System webpage. It's one of many online repositories for environmental product declarations. You can see some of the newer product declarations here. And of course, there's an entire library where you can search for EPDs for various products. So here we'll take a look at this one. This is, I believe, an air handling system for or a fan used in an HVAC system. And in this EPD, they break down the different phases of the product's life cycle. So here's raw material extraction, production, waste, transport, installation, use phase, demolition, things like that. And you can see the environmental impacts associated with each of these phases. So here's global warming potential. This is carbon impact. Here's water eutrophication, and many of the environmental impacts that we have just seen in LCA. So if you are incorporating one of these products into a building that you're building or into a larger assembly, then you can use this EPD to understand the environmental impact of that particular component. For an example of product carbon footprints, we're going to look at Lenovo's website, and they post product carbon footprints for many of their products. They manufacture laptops and desktop computers and things like that. So this is the product carbon footprint for this computer, and we can see that using lifecycle assessment, they have calculated the carbon footprint of this laptop to be 258 kilograms of CO2 equivalent, plus or minus 40 kilograms of CO2 equivalent. We see here that 76% of that impact comes from the manufacturing phase, and it's the manufacturing of these components. So 23.4 for the display, 20.6 for the main board. And then we see here that 17.5% of this carbon footprint is attributed to the use phase of the laptop, so consuming electricity, running, using the laptop. 5.3% is attributed to transportation, basically going from the manufacturer to the end user, and 0.7% of these emissions are attributed to end of life, so disposal of the laptop. And so both of these, the environmental product declaration and this product carbon footprint, these environmental impacts for both of these have been calculated using life cycle assessment. So we have reviewed life cycle assessment, or LCA. We focused on creating a life cycle inventory, but I'm sure you've had the question, well, how do you calculate the environmental impact of each of these inputs and releases? To answer that question, we will take a look at Eco Design Engineer, which is a role on the 3DEXPERIENCE platform that is part of the DS, or the Dassault Systèmes Sustainable Innovation Intelligence roles. One additional note is that there are other types of LCA. One type of LCA is economic input-output LCA, and this is where you calculate environmental impact per unit of spend. So you would have CO2 equivalent per dollar spent for a particular product, gallons of water per dollar spent for a particular product. This tends to be less accurate and is commonly used as an initial screening LCA to find hotspots and to understand where you would need to refine your lifecycle assessment further using process-based LCA to get a more accurate picture of the environmental impacts. Economic input-output LCA is also used for greenhouse gas reporting, often in reporting Scope 3 emissions associated with purchased goods and services or capital goods. And so you can imagine if you spent $1,000 on computers, there would be an economic input-output LCA emissions factor per dollar spent on purchasing computers. Thank you for watching my presentation. In part 2, we'll go over some considerations related to the 3DEXPERIENCE platform for using your SolidWorks data in Eco Design Engineer. And then in part 3, we will have a demonstration of Eco Design Engineer.